This is part 5 of a series on KNN. In this video, we'll look at how to use KNN to learn from data consisting of categorical features. The notion of similarity or distance for categorical data is not as straightforward as for continuous data. There are many ways to define similarity for categorical data, but in this video, we'll look at two of the simplest: the matching coefficient and the Jaccard coefficient. This video was produced in Korean and translated into English. The audio was generated by AI, text-to-speech. First, let's look at categorical data, which consists of nominal data and ordinal data. Next, we will look at the matching coefficient and the Jaccard coefficient, which can be used as similarity or distance measures for categorical data. Finally, let's implement the KNN classification model using the Jaccard coefficient or index. Now let's look at the categorical data. The continuous numerical data we have looked at so far is quantitative, while the categorical data is qualitative and consists of ordinal data and nominal data. Let's look at a simple data set like this. The data consists of 3 features and 1 target class, and all feature values are categorical. Ordinal data has a specific order or ranking. It can be subcategorized in order such as low, medium, high. The categories have a meaningful sequence, but the distances between the categories are not necessarily equal. You could say that medium is slightly larger than low, and high is much larger than low. Nominal data has no inherent order or ranking. The categories are just labels like red, blue, and green. For example, choosing red over blue does not imply that red is better or has a higher ranking. Nominal data can be converted into numeric data through one-hot encoding, and ordinal data can be converted into numeric data through label encoding. In this dataset, the values of the feature outlook, sunny, overcast, and rainy, have no natural ranking or ordering, so outlook can be considered nominal. However, the values of the temperature feature, cool, mild, hot, have a meaningful order, so temp can be considered ordinal. There is a clear progression from coldest to hottest. These categorical features can be transformed into numerical features as follows. We can assign a unique integer to each category in a categorical variable as follows. The feature temp can be considered as an ordinal feature and can be converted into a label-encoded feature as follows. These numbers are the unique integer values defined on the left. The features outlook and windy can be considered as nominal features and can be transformed into one-hot encoded vectors as follows. For example, sunny in the feature outlook is defined as the number 2, so it is converted to 001. The algorithms like KNN need to calculate distances between feature values. However, metrics such as Euclidean distance are not suitable for categorical data. Therefore, for categorical data, alternatives such as the Jaccard index are needed. We want to use the KNN classification algorithm to predict the class of this test data point. To do this, we need to measure the similarity or distance between this test data point and all other data points. Next, let's look at how to compute the similarity or distance between categorical data instances. The simplest way is to use the matching coefficient or the Jaccard coefficient. First, let's look at how to compute the simple matching coefficient. For two data instances x and y, the simple matching coefficient is defined as the ratio of the number of variables with matching values in the two instances to the total number of variables. The matching coefficient is more suitable for binary data. So we one-hot encode this dataset as follows. Let's compute the matching coefficient between the test data point C at the bottom and the data points A and B at the top. The number of matching variables between C and A is 2. And the total number of variables is 8. Therefore, the matching coefficient between C and A is 2/8. Since the number of matching variables between C and B is 4, the matching coefficient between C and B is 4/8. The matching coefficient between C and B is greater than that between C and A. Therefore, this test data point is more similar to B than to A. The matching distance is defined as 1 minus the matching coefficient. The distance between C and B is smaller than the distance between C and A. Therefore, this test data point is closer to B than to A. The matching coefficient has a problem in that it considers zero values as similar. One-hot encoding produces a lot of zero values, but that doesn't mean they are all similar. The matching coefficient is useful when values 0 and 1 are equally important. To improve this problem, the Jaccard coefficient was proposed. Next, let's look at the Jaccard coefficient. For two data instances x and y, Jaccard coefficient, or index, is defined as the ratio of the number of variables with matching 1 values in the two instances to the total number of variables minus the number of variables with matching 0 values. And the Jaccard distance is defined as 1 minus the Jaccard coefficient. The number of variables with matching 1 values in C and A is 0. The total number of variables is 8. And the number of variables with matching 0 values is 2. Therefore, the Jaccard coefficient between C and A is 0. The number of variables with matching 1 values in C and B is 1. And the number of variables with matching 0 values is 3. Therefore, the Jaccard coefficient between C and B is 1/5, or 0.2. The Jaccard distances are 1 and 0.8 respectively. Therefore, this test data point is more similar to B than to A. This is identical to the result of the matching coefficient on the left. Next, let's compute the Jaccard coefficient using the confusion matrix. In a confusion matrix, the true positive is the number of variables with matching 1 values. And the true negative is the number of variables with matching 0 values. Then, the Jaccard coefficient can be expressed as follows. Using the confusion matrix between C and A, the numerator of this formula is 0, and the denominator is 6. Then the Jaccard coefficient between C and A is 0. Using the confusion matrix between C and B, the numerator of this formula is 1, and the denominator is 5. Then the Jaccard coefficient between C and B is 1/5, or 0.2. Using scikit-learn's Jaccard score function, we can easily obtain the Jaccard coefficient as follows. You can get the same results as calculated by hand above. Next, let's compute the Jaccard coefficients for the label-encoded data. The Jaccard coefficient, like the matching coefficient, is also more suitable for binary data. However, the Jaccard coefficient can also be used for label-encoded data. The 1 versus rest confusion matrix for each label between C and A can be written as follows. The confusion matrix for label 0 and the rest of labels is as follows. The number of true positive is 0, and the number of true negative is 2. Using this formula as in the previous page, the Jaccard coefficient for label 0 between C and A will be 0. If we compute the Jaccard coefficients of label 1 and label 2 in this way, both will be 0. Averaging the Jaccard coefficients for each label gives the final Jaccard coefficient between C and A. This is 0. In the same way, calculating the Jaccard coefficient between C and B gives 0.11. Using scikit-learn's Jaccard score function, we can easily obtain the Jaccard coefficient as follows. When using label encoding, the average argument of the Jaccard score function must be set to macro. In this case too, this test data point is more similar to B than to A. The Jaccard coefficient is an improvement over the matching coefficient, but it also has its drawbacks. One of the drawbacks is that it doesn't take into account the frequency of occurrence of each label. For example, if your data contains a lot of label 2, you will have more instances that are similar to the test data point, because they are more likely to match the label 2 of the test data point. To solve this problem, you need to consider the frequency of occurrence of each label. We'll look at this in the next video. Finally, let's implement a KNN classification model on categorical data using Jaccard coefficient. Let's use the following simple dataset that was used in the previous examples. This dataset consists of categorical features. It was taken from this site. The names of each column are as follows. Now we write a function that predicts the class of the test data. The input X is one-hot encoded or label-encoded feature data. And the input Y is the target class. K is the number of neighbors used in KNN. The input average is the argument used to compute the Jaccard coefficient and is specified as binary or macro. Take data instances one by one from feature data X and generate test data and training data. In the first round, we use the first instance as a test data point and the rest as training data points. We compute the Jaccard similarity between the test data point and all other training data points, and store the result in the similarities list. Then we choose the K neighbors with the highest similarity to the test data point. We predict the class of the test data point by majority vote, and we store whether ypred and ytest match or not in the match list. If they match, true is stored, otherwise false is stored. The ypred is the predicted class, and the ytest is the actual class. Print the prediction results to the screen. In the second round, we use the second instance as a test data point and the rest as training data points. This process is repeated until the last instance is used as a test data point. Finally, we measure the accuracy using the true and false values stored in the match list and return the accuracy. If there are 7 trues and 3 falses, the accuracy is 70%. Now, let's use the function predict to classify the categorical data. First, we one-hot encode the data. The encoded data is as follows. The last 2 columns are the encoded target classes, and the remaining columns are the encoded feature data. The variable X is the encoded feature data, and the variable Y is the encoded target data. You can use the last column as your target data. The K value of KNN was set to 5. We measure the accuracy by calling the predict function we just wrote on the previous page. Since we used one-hot encoding, we pass binary to the argument average of the function Jaccard score inside the function predict. The results are as follows. If we use the first instance as a test data point, the true class is 0, and the predicted class is also 0, so they match. The results for the remaining instances are as follows. 11 out of 15 are true, so the accuracy is 73.3%. Next, we'll use label encoding. The encoded data is as follows. Using this data, we do the same thing as on the left. The results are as follows. In this case, too, we achieved an accuracy of 73.3%. Let's run this code. The results are as follows. So far, we have looked at the matching coefficient and the Jaccard coefficient. In the next video, we will use the IOF distance to classify categorical data.